I am pleased to introduce our speaker today, the friend of CII, Dr. Pingbo Tang. He is with Carnegie Mellon and is a professor in their engineering department. So I'm going to go ahead and pass it over to him, and he will give you some information. Again, we'll take questions at the very end. Thank you.
Thank you, Jenny, for the introduction. Special thanks to CII to give me the opportunity to present to the audience. Big thank you first to CII, to my institution, funding agency, collaborators, students. Before I start, I would like to introduce a decision-making scenario. Decision-making could be on a cyber system, for example, PWSA, which stands for Pittsburgh Water Sewage Authority. They are mapping the lead service line in Pittsburgh. And the green part is the one has been finished on a GIS system. The blue part is ongoing. And of course, there are some red parts which is still under planning. Then on that system, and the Pittsburgh people try to understand how many lead service line of water has been replaced and how many of them they are still ongoing, how many of them they are under consideration. Then from that, people need to carry out the plan in the field. Human physical system means people replace the sewage line, the water service line, distribution line in the field. Now, once we have a map, which is a digital map, once we have a physical system, people carry out the work. Someone say, okay, why don't we combine the physical view and the cyber view together and provide the human a decision-making tool in the field. So in this case, a lot of you already know the augmented reality overlapping the design or any virtual information on top of the physical field of view of a worker. Then people call this human cyber physical infrastructure system. If we look at this decision-making process, the water system has a lot of changing parameter, like how fast the water is moving, the quality of the water, the weather, and the human want to make a decision about, okay, let's control the water system. When we are replacing a lead line, then we need to be careful about a particular. Then once people make all those decisions, there is a decision-making process. So that process has two parts. Number one, human relevant. And people need to recognize things, analyze things, communication. Of course, there is something which is human irrelevant, computational, sensing, visualization. And these two processes combine together, and the human machine racing with the real world changing, the water system changing, and the real progress of the process of replacement of the lead lines. Then we need to race ahead of time to make sure that we got enough time to make reactions. And if we didn't get enough time, then the reliability of the system would not be very high. And in this case, I use a very high-level equation to present the information about the two levels of racing. The first level, we're racing at the individual person level. The worker do the job fast enough than the deadline for the task assigned to the worker. So which is the left part. The right part is the team of worker, including their individual tasks, as well as their communication time. They have to make sure that all these things has to happen within the deadline for the group of tasks. Then once these two things at the individual level, at the team level, both satisfy the timeline, deadline, then we are going to say this is a reliable process. Then we use the P stands for the probability, individual level and the team level. Both things should work and should be within the deadline. A lot of things happening in the real world, we can measure like using this probability concept. And there is a lot of things happening in the real world as a human get involved in this process. For example, today we're going to talk about the nuclear power plant outage control, which is a problem of refueling of a nuclear power plant for maintenance purpose and for refueling the reactor. And in that case, a lot of people working on the site, and there's a group of people in the control center make decisions to make sure that multiple tasks, they are not going to influence each other in a bad way. Another even more dynamic process is called air traffic control. The control room is the control tower of an airport. And the air traffic controller observing the landing and the departure aircraft and making sure that they are not going to get into the same runway. For example, 2018 in Shanghai Pudong Airport, because of a communication problem between the pilot and the control center, the Delta airline aircraft is leaving, but at the same time, they saw there is another Japanese airline aircraft stopping at the intersection and stop that departure path, which is very dangerous. Then once we look at those, it's a teamwork. It has multiple people, pilot, air traffic controller, outage center, field worker. Then we look at the cyber system, physical system, and the human system. So the cyber system, we talk about the control digital center and someone called control room. And the control room can be an analog center, like people has been built many, many years ago for nuclear power plant or for many other large facilities or process plant. And there is a physical component. People need to go to the field, observing the workspace and making sure that everything is okay. And because some of those information might not be measured by sensors remotely. Then human part could be a controller in the control room, could be the field worker in the field. Then once we combine the field observation and the remote action, that means we have an integration of a cyber-physical view and to provide a decision-making tool for the humans. And the human can be controller, field worker, or in the future, is the controller and the field worker, they're the same person. Then once we look at this in a different direction, and we can see there is multiple dimensions. Because in this component, we have a H, human, C, cyber, P, and physical. Then for each process, we have 3 steps: cognition, recognize things, decision-making based on the information we have when we make a decision. Last one is to carry out the task, like execution. For each one, it's possible to have a human-human interaction, human-computer interaction, and a human-physical work interaction. And each of these could have implication for reliability, for safety, and efficiency. Once we look at those safety and efficiency problem, like what we mentioned in those 2 examples before, and I look at human physical, human cyber problem first. And the communication problem is also important, but there is a lot of researcher who is going to do a lot better work than what we have done in this project. And we look at the first 2, operation reliability, digital control reliability, in our research for nuclear power plant control for individual worker. And that worker, the goal is to make sure that they can be a controller, at the same time it's a field worker. So once we look at this problem, as I said, we can talk if we have infinite amount of time for communication, because that's a whole lot of communication study out there, and which is more, they got more communication data and analyze the communication flow. And we focus on the field worker control room and how to combine them in this research for efficiency and safety of the operation of nuclear power plant. Then why this problem is important? Safety and efficiency, of course, it's a critical component for decision-making in nuclear power plant outage control. An outage usually takes 20 to 30 days, and it could be 2,000 plus refueling activity, and there is 2,000 workers in the field, possibly at the same time. Then once those people, they are doing different things, we need to make sure that are they carrying out their procedure, and when they are making decisions in the field in an improvised way, for example, they deviate a little bit from their manual, or their timing is slightly different, it might influence the safety and the efficiency. Usually, people go with the conservative approach. They just wait and talk to other person to make sure that, okay, are you doing that? If no, I'm going to wait. So that usually compromises efficiency for the safety. However, the efficiency is expensive for this case. This case, it's in Phoenix, and it's a large nuclear power plant, and it provides 75% of electricity for Phoenix, which is a big city. Then if the delay of the refueling process takes more than 20 days, each day, based on their estimation, cost 1.5 million. Because of losing that reactor for 1 day, it's expensive for Phoenix because we need to get electricity from elsewhere. So the challenge is, are we able to provide those workers with sufficient information to allow them to understand what's the cyber world and what's the physical world and how to do things in the right way at the right time to achieve safety and efficiency at the same time? That's difficult. Let me show you what happened. In the nuclear plant field, and the people usually have a control room and has a digital control system and get information from the sensors. Then, based on the sensor signal, send the control signal to the field and to remote control what should happen and what should be on, what should be off. Sometimes the sensor might not have the correct information because of noise or because of the missing value. Or some of those observations, such as there is a little bit water here and there is not enough space and enough space there, or there is something which is not measured in the field. The field work operator is going to be the critical component and to work together with the control room operator. And the control room operator give the operator some tasks, say, okay, you go there because you can collect some information the system sensor network might not have, and the human, we trust them better. Then the human go to the site and do the operation and to finish the work because they're more trustable. But sometimes they need to communicate back to the control center, say, I'm done. However, there is a few places which might cause issues. For example, the manual, the procedure might have some kind of like a imprecise information. Even for nuclear power plant control, procedures could be ambiguous for some of those workers. And some people might see something they could like interpret in the field in a slightly different way. And that causes human errors. They might miss critical information in the field. The human might not notice something and cause issues. Then we are trying to understand, okay, if we have a macro level decision maker in the control room, maybe the person in the field should have a macro view and to get a lot of comprehensive view and a lot of more information to augmenting this person who are in the local view. So that this person will pay more attention to something. If they know it at the bigger view, they will pay more attention to something related in their local space. Then the case is to use the control history to support the local worker so that the worker somehow to become a controller and the field worker at the same time. Then in this case, we can have the operator replace part of the controller's job. And to understand, we need to do navigation based on the larger picture. And we understand what is the critical component I should touch, I should not touch. And what is the trend prediction of the system to capture the dynamics of the nuclear power plant for safe operation and to stop at the right time or to start at the right time. Then in this case, if we want to allow those people to know where they are and what they're doing, and the computer vision technology usually support them to understand where they are and how to navigate to the right place, how to recognize the right component, and to match the digital object with the physical object that's seen on the site. Then that combines them into a physical view and a cyber view for safe, efficient, and reliable operation. Then I have a quick demo about how this system should work. It's a demo for a nuclear power plant training facility operated by Duke Energy. And we use the laser scanner to create our point cloud and a digital world to allow people to specify 2 tasks, which should be start and finish, then start task 2 at the second place. Then the worker is going to be able to look at the big map and use the information from the digital model to identify what is the correct component, like a valve that should operate for task 1. Then they will go back to the big map and move to location 2, and to find out there is a few things along the way they need to move and avoid and find out the right component they need to operate. So this demo helps us to understand what's the vision. And a more technical vision is we are going to support a person who has the control history as the input and the real-time information as the input as well, to reasoning about what's happening in the field and what happened in the past. Then use those information to produce output to guiding the worker to know where they are, work location, the critical object they should be pay more attention in the field, and to guide them to do operation in the correct order at the right timing. Then predict if they do this, what's going to happen, and to provide them information about the risk, and to do compliance checking. Someone is going to ask, why don't you have a machine to do this whole thing autonomously? That's a good question, and we can discuss that for a whole day. But I would say autonomous control is like autonomous car, control of a large process plant, nuclear power plant, which has a lot of interconnected systems together. It's even more complicated than control a vehicle. Then at this moment, AI has not achieved the autonomous control of that type of large, complicated system. And the AI is able to do a lot of control, autonomous driving now. Maybe that's the future. So we come back to this solution. We have the human and have the information delivered to the human, and the trust the human could use those information to make a better decision. Then we focus more on how the system should provide the human with sufficient information. Then in this case, we talk about context-aware safety information display for nuclear field workers. So that's a big vision. Then in this case, we have the research area. We need to understand human, how reliable is the person if they got the information and what they are going to do, and how reliable they are going to carry out the procedure based on the real-time information they have. Then we need to model the process of work process to be able to understand what they're doing. Then we also need to understand what's the safety of those procedures and the different options when people are doing different things. So that's the research area. And we have a multiple technique I'm going to present today to mention how we are enabling such kind of context-aware safety information display for the field worker who has a partial role of controller. Then the technique could be sensor log analysis, which means we get the bigger view from multiple sensors to support human decisions about what is the right time to do a certain operation action. We also need to get the human perceptions about the safety and efficiency of certain operation context, and understand as a human what they think is more important in terms of safety and in terms of efficiency. Well, of course, we look at a lot of those text-based data, like work package description, work order description, accident report, and to do natural language processing to analyze what happened in the past and how the system should help people to do right thing based on the documented history in text. Then computer vision can support augmented reality glass and to understand what are the information the object should be detected as an important object, to guiding people to look at the right object and to make sure that's the right object at the right time to take the action. Then the outcome is going to be our AR glasses and help people to have a real-time guideline based on the real-time information, saying, okay, based on the real-time information, that's the right thing we should do for safety and efficiency. And the first part is the sensor log analysis. And we do have tried some technique to analyze the control history. For example, in this case, we used Aramco. It's a nuclear power plant simulation software to simulate the sensor readings and to simulate the start and shut down process of a nuclear reactor. Then from this case, the basic idea is to say when the sensor reading is like this, and we are assuming that when people see sensor reading, it's let's say we have 10 or 100 sensors, and the sensor reading achieved to this value, and the human said that's a context. I should taking this action. It's more like a human drive a car. They look at the dashboard and see certain things on the dashboard, they are going to take action. Then we look at the skillful person's control history and to label this is a successful control and this is not a so successful control, and to train the machine to understand when they should wait, when they should turn on a valve A, and when they should change the length of the rod inside the reactor. And the prediction actually, to be honest, is not very good, because look at the precision and the recall, and the precision for many algorithms, even the best algorithm we tried so far, it does not achieve like a 100% precision and the 100% recall at the same time. What is precision? Precision means whenever I say you should do this, then it's 100% correct, you should do this. Recall means, did we capture all the times you should do this? If we didn't, if there is a 10 times you should do this, but the algorithm only capture one of them, even though the algorithm say that one time is correct, it's not so good because we only capture one time we should do that. So we need to have a high precision and high recall. Not all the algorithms didn't achieve that, but we noticed that if we have some kind of technique to resample the data, and we significantly enhance the precision and the recall for some of those prediction of control the feed A, the feeding water valve, and the latched AUC. So those control actions has a much better prediction timing compared with the raw data. We didn't have enough data for feed A, feed B, and the latch. Those are very rare actions. For example, we have a lot of actions saying you're waiting, but we might not have sufficient samples in the control history say you need to turn on this. And maybe that's for one session, it's only one time you push a button. So there is not enough samples to do this. And we use this resampling technique to increase that type of sample and improve the performance of this type of prediction to allow the algorithm to understand in this situation, people should turn on the feed A. So we know the computer algorithm is not perfect, and even the sensor log analysis shows some potential, but we still need to ask people. Then we ask those people, say, okay, what you see and what you think about the factors influence the safety and efficiency of operation for a given context. Then those questions we ask, and we keep in mind saying, what are the stages involved in nuclear power plant field operation? And when somebody make a mistake, too early, too late, or they miss certain operation, what are the mechanisms about the human error occurrence? And what are the factors involved in each stage of operation for safety and efficiency? Is there any root cause of those mistakes? And once we look at this, we first has a phase 1 study, look at those documents and find out MPP event report. It's called licensee event report. And to find out research papers documenting some of those accidents in the history. And use those to produce an ontology and to summarize a comprehensive list of factors influence the safety and efficiency of nuclear power plant operation for different scenarios. Then for phase 2, we design a survey and use those questions we generated from phase 1 and to distribute the questionnaire to the domain professionals. Then we got a lot of people reply and fill out the survey. And phase 3, we look at the survey results and use those results and bring those to a discussion. and to interview a few people who are willing to participate. That number is smaller than the number participate phase 2. So we call this modified DEFI study. So this is the comprehensive list we identified from our literature review, event report review, and we find out there is a multiple element and their attribute we should mention in the survey, and to help people to understand what attribute of what kind of things is related to safety and efficiency. For example, of course, the operator, they can perform control action, and the action should have how long it's going to take, what is the time interval, and what equipment they are taking action. Then it goes to the equipment on the right side. You can see the equipment, what's their name, and what is there any limit of this equipment, and is this equipment has some special hazard based on the manual, and what is the response time of this. Then there is a supporting tools, and in the middle there is also a record and about the history of those equipment and the past, how long it's going to take people to walking from one location to another location. Then for each of these, you can see there is on the right side the limit, and the limit could be upper limit, lower limit, and could be different kind of hazards, and the response time, exceptions. For example, in some scenario, you should pay attention to the rules of safety, but in some cases it's an exception. Then at the end, it's a scope, and we're going to say this is a stepwise type of a regular, process control, or it's more like a procedure-wise, or it's a regulatory, or it's an administration process. Then we answer those questions by asking the domain professionals, and we find out for a typical work order for nuclear power plant operation, they have 6 stages. And I put them here, the job debriefing, walk down the procedure, and they have a placekeeping, and walk to the target location. And whenever they have something, they need to respond to the event they discover in the field, which is not predefined. Then they implement the response. And for each of those phases, we organize the questions to mention about those factors we summarize from the literature review into questions to say, okay, in this phase, what are the factors you think it's more important compared with others? Then in this case, we look at safety and efficiency because we have a survey section for safety and a survey section for efficiency. And look at the emphasize, if we emphasize safety, if we emphasize efficiency, how things are going to be different. Then we have the people to go comment on the survey results and tell us why they respond that way. So this is the distribution of the responses from the country. And we have a 33 participate phase 2. And we have 11 participate phase 3, which is an interview, the DEFI second stage. And once we collect their responses, and there is a lot of a question answer scenario, and there is description of those questions. So for each of those phases, phase 2, we have a safety-based survey, efficiency-based survey. Each of those have 98 questions. When we go back to here, we can see that 10 questions for pre-job debriefing, and those parentheses are the number of questions asked for those phases. Combined together, safety, 49 questions, efficiency, 49 questions. In total, could be 98 questions. Then for those 98 questions, we've noticed that some of those questions may talk about a similar thing. Then, for example, if this is talking about the critical safety issues about a toolbox, then people might look at this same toolbox from different dimension, or they mention the same issue using different language. Then we use something called exploratory factor analysis to find out what's the redundancy and reduce those like a duplicated information from multiple questions and answers. Then that process reduce the dimensions of the factor analysis and identify a few critical factors three group of factors which are emerging from that kind of like a dimension reduction practice. Dimension reduction practice is just like what I said, reduce the duplication, redundant information, and just say those question answers are talking about the same thing. And those same thing has a three category: workspace dynamics, such as the physical space, layout, location, dimension. Those are the things people mention all the time for the spatial domain. And also talk about how those spatial layout change. The other one is about the workflow prognostics, which means as a mechanical system, for construction site is also similar. You have those equipment, the workflow might evolve and have a relationship of finish start or start start. Those kind of relationship, their function can influence each other. Then we need to understand what's the function of the component in the flow and how they influence each other, what's the dynamics. Then the last one, of course, is the hazard. It could be something people labeled as a confined space. It's a controlled release of energy, heat, pressure, and holes. Of course, people should avoid those areas because of falling risks. So these three categories forms the four major dimensions we are studying. And we go back and interview those people and find out that there is very, very interesting emphasis on safety compared with the emphasis on efficiency. On the left side, you can see the three categories are emphasized by people when we are doing the safety-oriented survey. And for example, you can look at the walk to the target work location. When we emphasize safety, they emphasize the dimension, it's a hazard. People walking and they need to pay attention to hazard. That makes sense, right? But for the same thing, if we say, okay, we need to pay attention to the productivity, then immediately you can see that the workspace dynamics show up. At the same time, we still need to pay attention to hazards. And a lot of those findings is documented in our research report, and we can compare all those responses. The point here is that for different phases of the operation, people might emphasize maybe they need different information. As augmented reality devices, we cannot just deliver them all the information. What we should do is that we need to understand for different phases, what's the right time to deliver what category information to the person for supporting their decision making. For example, if we emphasize safety and productivity at the same time, then we may not want to provide a lot of details about workflow prognostics because based on this survey, walking to the target work location, there is not too much emphasis on workflow prognostics, but that kind of information, workflow information, is important for response planning and response implementation. Then for that case, we have to provide hazard information and the workflow information, and not too much about this workspace dynamics. Then once we have those perceptions from human, that's a very high level. Then we need to go back to the natural language and to see those reports. And because as a human, we cannot read that much, but if we analyze those work package description, work order description, using natural language processing, it can empower us to see more and to see what's the process pattern about how things happen and how people specify the procedure. Then in this case, we look at the work package description. For nuclear power plant is the operation procedure. And we use some natural language processing algorithm to produce a work package database, which can be interpreted by computer as actions of control. So one action could be, for example, you can see on the right side, determine if the control bank D, the rod height is a certain value. So that's our sentence in the operation manual, and it can be interpreted as an action in a specific context should happen. And so this is the algorithm we tried. It's called BERT-based model, and has a conditional random field layer to produce the output and to parse a sentence into different type of things, like the object to be controlled, and what is the control action, and what is the limit of the controlled value. So the algorithm can produce something like a knowledge graph from the work order description or from the historical report. For instance, the maintain action will have constraint, say, control the steam dumps between 555 and 559 Fahrenheit. It also has the component property extracted from the work order description. A component could have auto, and the function is for startup and need to be verified. And on the right side, it's a control action. You can see it's a manipulation for the rod height, and the people need to control the rod height. And also for the main steam system, we need to look at the warm-up process. So this is the ongoing work. We extract such information from some work orders, but there's a lot of things we need to do, and the accuracy of extracting the control object actions is pretty high. It's 90 or even close to 100 in many of those work orders. But the challenge, the real challenge, is to find out what's the procedure and what's the pattern of a successful, and how to constrain people's reactions using those information from the historical manual operation accident report, and to help people to understand, okay, this is what they mean you should do to follow this procedure, and what are the limits of those values. And so in that case, we produce the work package database is not the end. We need to reasoning about those work package and to produce the hazard area. And whenever you have a workspace, we need to find out what is the safe path to come from point A to point B, and how much time you have to finish those tasks. So those are the real-time guidelines we should provide to the worker to tell them, okay, these are the areas you should avoid, and this is the safe path, and you have 10 minutes. Then digital model, building information model is useful. And we need to match in the build information model with the work package database to find out, to reason about those information to produce a path for safe and efficient operation. So that's the ongoing work. Then once we know that, we know we need to understand this is the kind of like a guideline for people to do things. And we also want to understand what are they really doing. And if we have the video to show their local workspace, and we have a video to capture how they are moving, computer vision algorithm allow us to do positioning, to find out what's their current location, and to help them to do navigation, which means they know where they are and what's the next task and where they should go. Then they need to display the right information for them to navigate, identify the right object to operate. So this is a very challenging problem, because we are not going to assuming in such kind of like a facility, we always have good Wi-Fi signal for indoor navigation. And we are assuming that we only have an iPad or iPhone or mobile device or augmented reality device that has an IMU, which is an inertial measurement unit, measuring the acceleration in XYZ direction and the rotation gyro. And we have the image taken by that device, and use the IMU to help us to augmenting the information from the video content and to guess where they are. So we have pretty good success for most of the areas, but still have some challenges. If you look at the red line here, you can see those people, the person is moving, and the algorithm can tracing how this person is moving. And at the bottom right corner, so that trajectory actually is not very, very precise, because starting from that point, we got a big wall, and the wall does not have too much features. Computer vision algorithm need to have features on the wall, say there is a door, there is a corner. If it's a white space, then the algorithm will lose track if the feature is not enough. We are still trying to overcome those issues by pasting some of those like a chessboard on the wall, because those can add features in those environments. So combine those things together. We can have a HoloLens augmented HoloLens to support people do real-time decision making in the field. I'm showing you a very quick demo about our research student has been working on in a mechanical room and to demo the capability of the system. So here you can see if we have a context-aware operation support, and we allow people to get the information at the right time for efficiency, and we also get that information to make sure that what they're doing is safe. Then, for example, here, they need to have the key functionality. If you want to reach that space, you need a ladder. And the operation time, the operability index, which is like a theoretical concept we generated from this research to measure how complicated is a task, how demanding is a task, to provide the worker a guideline to say, okay, what kind of functions you need, where you are, what tools you should bring, and how much time you have. Then once the worker has those information, they can start moving to the right location, and they'll move to the location by look at the map and start to move. Once they move to the into the workspace, the augmented reality device will highlight the green, which is the destination mark, and say this is the valve you should look at. Then with those information, the power of this is to have both the physical world and the cyber world together, and with the real reasoning support, and to help people to understand what's going on and what's the safe thing and what's the right timing to do these things in this dynamic workspace. So we look at those issues and we back to the domain. And we are looking at the control issue from the cyber world to connect to the physical world. And we need the worker to get access to the real-time information and also the historical data, and provide feedback to the control room. If we have a control room in the future, right now we still have a control room. The ideal thing is like, we may not even need a control room in the future. So similar problem happens for facility management. They have a control center, and the people communicate with each other about the air conditioning system and which part of the water system has a leaking or has an abnormal temperature issue for certain rooms in the campus of Carnegie. So the challenge of this, it's amazing. We look at the historical report, but we also should not forget about the regulation, and to find out how the historical report regulation combine together with our building information model to provide real-time decision making. And we should not forget about human, because human, usually it's still more trustable, understandable than AI algorithm. And we need to trace an experienced person's behavior and to ask them to teach us in what situation and why they do certain things at what time. And I would envision the future. We have a building information model from the basis, and we have a simulation algorithm to help us to predict if we do certain things, what's going to happen. Then we support the process of recognition, decision-making, physical process execution as a cyber-physical integrated process. Thank you.
Okay, wonderful. I was just looking at the questions, and it looks like we only had one, and they wanted to know if your presentation would be shared, and the answer is yes. We are going to post both the slides and a recording of this presentation, I'd say by the end of the week, on CII's website. If you click on the blog, it will exist right under there. There's past webinar presentations and blogs are found there. But I think you'll,
as long as CII feel like I provide this CII logo is appropriate.
Perfect. Yep. We can make sure that your slide deck gets out. And otherwise, oh, we do. We have one more question. Have you tried ADASYN resampling technique versus SMOTE?
We haven't, but that's a good thing. And I thank you for the suggestion. We didn't try it because we resample using SMOTE, but that another resampling technique might be much better than SMOTE. Yeah, for our data set. I don't know.
Thank
I
you,
don't know which
Edwin.
one's better. I don't know.
That's a good question. So Edwin has a follow-up. He says, in general, from my experience, it's better.
Oh, really? Okay, so that's good to know. Because of my limited knowledge about the sampling, and I should try. Thank you.
Okay, of course, we have another question coming in. Can your approach be used for the petrochemical industry? Of course, lots of the CII members are in that heavy industrial space.
Yes, yeah. I will be more than happy to approach to the petrochemical industry. We already approached the water industry, and we actually have some water treatment plant digital twin, which is very similar as the one I presented here, because we are focused more on the fundamental issue about cyber-physical information integration for process plant. Based on my very limited knowledge, process plant could be a nuclear power plant, and the nuclear power plant has a water system. And the nuclear power plant might also could be replaced by a chemical process plant. I didn't see any problem to approach that domain and to find out what's the challenge there. I believe besides this fundamental challenge I explored in nuclear industry, there is a lot of domain issues because those are chemical process I'm not familiar yet. Yeah.
Good answer. Any other questions? I'm not seeing any come in. So if you do have questions, feel free to let us know. You can always reach out to me. You can find me on the CII website, and I will connect you to Dr. Tang. Well, we do appreciate your attendance today. I know this was a well-received topic. Not a single person dropped through the entire webinar, which is very impressive. They appreciated the content today, Dr. Tang. We do thank you for your time. We appreciate everyone tuning in today, and we hope to see you at CII's next webinar. Enjoy your week, everyone, and we hope to see you in San Antonio this summer for the 40th anniversary and CII's annual conference.
I will be there. Thank you.
No. Oh, perfect. They're saying thank you in the question panel. So thank you all.
Thank you. Thank you.
Enjoy your day, everyone. Take care.